Find the area of triangle ABC in square feet. In this problem, the length from point A to point B was measured at a temperature of 105 degrees Fahrenheit. The length from point C to point C prime was also measured at a temperature of 105 degrees Fahrenheit. Both of these measurements were made using a steel tape which was calibrated at 53 degrees Fahrenheit. Also note that angles C, C'A and C, C'B measure to be 90 degrees. Therefore, we've effectively been given the dimensions for the width and height of the triangle. To find the area of an oblique triangle, ABC, we need to determine the appropriate area equation to use. We'll begin by defining capital A, subscript A, B, and C as the interior angles of the triangle at points A, B, and C, respectively. Also, lowercase letters A, B, and C will refer to side lengths on the opposite side of the triangle from the angle of the same letter. On to our area equations. If we know the measurement for angle A and side lengths B and C, then the area of the triangle can be calculated as 1/2 times B times C times the sine of angle A. This equation can be modified in the event angle B, side A, and side C are known, or if angle C, side A, and side B are known. A second equation to find the area of a triangle is if all three side lengths are known. Then the area equals the square root of the product of S, S minus A, S minus B, and S minus C. This is called Heron's equation, whereby the variable S equals the semiperimeter of the triangle, or 1/2 times the perimeter of the triangle. A third equation for the area of a triangle is when all three angles are known and the length of one side is also known. If side A is known, then the area equals A squared times the sine of angle B times the sine of angle C divided by 2 times the sine of angle A. This equation can also be modified in the event we know the length of side B instead of side A, or we know the length of side C. The fourth and final equation for area is the one we'll use for this problem, where the area simply equals 1/2 times the height times the width. So, returning to our problem, we need to determine the actual height and actual width of triangle ABC after it has been corrected for the temperature difference. In this problem, the true height of angle ABC equals the length of segment C prime if it were measured at 53 degrees Fahrenheit, which is the calibrated temperature of the tape. However, we only have a measurement of line segment C prime when the temperature is 105 degrees Fahrenheit. Therefore, we'll equate the height of the triangle to this measurement plus a temperature correction distance, C. In the same manner, the actual width of the triangle will equal the width if the measurement were taken at the calibrated 53 degrees Fahrenheit, which will equate to the measurement taken at 105 degrees Fahrenheit plus a temperature correction distance, C. Since we know the height and width of triangle ABC at 105 degrees Fahrenheit, we need to solve for the temperature correction distances. The temperature correction distances equal the temperature during the measurement minus the calibrated temperature times the measured length times the coefficient of thermal expansion. Since the problem states the tape is steel, the coefficient of thermal expansion, alpha, equals 6.45 times 10 to the negative 6 degrees Fahrenheit to the negative 1. And after plugging in the values for the temperatures and lengths, the temperature correction distances equal 0.068 feet and 0.147 feet for the height and width, respectively. We'll round these values to the nearest hundredth of a foot, and after plugging them in, as well as the measured lengths at 105 degrees Fahrenheit, the actual lengths for the height and width of triangle ABC equal 203.63 feet and 438.31 feet, respectively. Plugging these values into our equation for the area of triangle ABC, we find the area of the triangle equals 44,627 square feet. When reviewing the possible solutions, the answer is C.